Hello, this video is on hypothesis testing for the mean population standard deviation unknown. So if you have already studied confidence intervals prior to these videos on hypothesis testing, we're bringing back the t-distribution that we used for the confidence intervals under the scenario of these conditions. Now your population has to be normally distributed, and the population standard deviation is unknown. We use the sample standard deviation, S, as our standard deviation. Usually this applies to small samples and is less than 30, but if we don't know the population standard deviation, it's still technically correct to use the t-distribution. Now you may recall from the explanation on the t-distribution is that as the sample size gets larger and larger, the t becomes the z as it gets larger. But I mentioned here, so that's not always the case. So it could certainly be over 30 and still be the t-distribution. Alrighty, so let's bring back the t chart that we've used even for the hypothesis testing for large samples. Now, similar to that, everything's going to be the same here, except we're going to have to bring back our degrees of freedom idea there, the n minus 1. So one-tailed on our chart covers both left-tailed and right-tailed. Well, it was taking too long to bring up that chart. I'll just go back. One-tailed is both left-tailed and right-tailed, and then we have to include a negative sign with the value that's for the left-tailed. And two-tailed gives us a plus and minus sign with each value when we're looking up critical values. And the wording for the decision rules is the same for both t and z. If it's left-tailed, you're going to reject the null if t is less than the negative t critical value. Right-tailed, you're going to reject the hoe if t is greater than the positive critical value. And two-tailed, you're going to reject the hoe if t is less than the negative or if t is greater than the positive. Now, one thing I want to mention about the t-distribution is we're pretty much going to work with the decision rules for this. P-values, they kind of require technology, and you'll see them in the calculator, but you won't be asked, certainly on any of my exams, and I'm pretty sure I've eliminated those from the My Math Lab homework, where it asks for the p-value for a t-test. That can only be done with technology. See, for the z-test, we were able to look those up on the normal curve, the cumulative normal, we could get the p. So that was fair to everybody. But this is if you don't have, so we're just going to use this decision rule method only to decide whether or not we're going to reject or fail to reject. So let's practice looking up the chart here. And I'll go to the bigger chart. These are kind of small, but you can zoom in on them later if you need to. But we got to say we have a left-tailed test, and alpha, the level of significance, 0.10, and n equals 11. Well, if n equals 11, remember degrees of freedom, just like confidence intervals, is n minus 1. So it's 10 degrees of freedom. So we will look up. Left-tailed will be on the one-tail part of the chart. Left-tailed makes it automatically a negative. So let's see if that chart came up there now. There we go. So 0.10, one-tailed. And let's come down here. 10 degrees of freedom is right here. But it's going to be negative. So it's negative 1.3722. Therefore, your decision rule statement would be as follows. As you can see how it's written from back up here, like so. For left-tailed, it's written in that form. So you see we have reject the hoe if t is less than negative 1.3722. All right. Right-tailed test with alpha 0.01. N is 22 degrees of freedom. N is 22, so we have 21 degrees of freedom, excuse me. And then because it's right-tailed, it's automatically going to start out as reject the hoe if t is greater than some number. and it's going to be the positive value when it's right-tailed. So I want to go to 0.01, one-tailed, 21 degrees of freedom. So 0.01, one-tailed is right here. So it's the next to the last column on the right. So when I scroll down, let me check. Double check the degrees of freedom being 21. And it is. So 21 degrees of freedom, second column. There it is, 2.5176. So we would reject the hoe if T is greater than 2.5176. And that's, so you see they're here in small print. Obviously, there's that one circled. Next one is two-tailed, 0.05, n equals 7. So we have 6 degrees of freedom. So we're going to reject. It's always a double-worded thing with or in the middle. Reject if T is less than a number or T greater than a number. There might be one of a homework problem, or maybe I've eliminated it by now, but where they actually use they usually use and between the two words instead of an or. That's a mistake, but if that's the only one that splits them up like that for a two-tail, then it would be the answer you would want to pick. No way on an exam is that going to happen. But it's supposed to be the word or, not and. And implies it can happen at the same time, which is impossible. You can't be less than a negative number and greater than a positive number at the same time. So, two-tailed. Two-tailed, 0.05. Got to be real careful here, just which row you're on, because there's also a one-tailed 0.05. Two-tailed 0.05, 6 degrees of freedom. That gives me plus and minus 2.4469. Okay. Now let's take a look at performing a t-test using critical values. And notice I mentioned only critical values. Now when I do this in the calculator, we'll make note of the p-value in the calculator, and I'll just show you, but I'm just telling you that you're not going to have to get the p-value. The test statistic is pretty much the same thing for T as it was for Z. The only difference is they have the sample standard deviation S instead of sigma down there on the bottom, but it's exactly the same. So we sort of do pretty much the exact same process as you do the Z. Just, you get your critical value differently than you did for the Z. Everything else, the same. Alrighty, let's take a look at this example. A computer repairer believes the mean cost for damaged computer's repair cost is more than $95. To test this claim, you determine that the mean repair cost for 7 randomly selected computers and find the mean repair cost is 100 with a standard deviation of 4250 at alpha equals 0.01, which is the level of significance. Do we have enough evidence to support the repairer's claim? Assume the population is normally distributed. All right, that's just thrown in there at the end. It could have been put in there anywhere to validate using the t-distribution. Of course, if it wasn't there, we still would use it anyway, but kind of needs to be there to make it official. Sometimes you'll see that in homework problems for confidence intervals and hypothesis testing. In the My Math Lab, they'll have a part there, okay, what condition must be met for this? And that's what you're looking for is the answer. So let's look at the ho and the ha statements here. We got a more than. More than means greater than. That was our claim. Greater than's a ha, because it doesn't have equal, and it pairs up with less than or equal to. So we have less than or equal to 95, and then greater than 95. Now they're asking us, and I just wrote the basic data value stats they gave us right here. And just wanted to mention then, keep in mind, since this claim is the alternative, if we're supporting the claim, if we end up supporting the claim, that will mean we had to have rejected the hoe. Just pointing that out to you. Let's come up with so what we have to do is come up with a decision rule. Then we have to calculate our test statistic, then decide whether or not we reject. That's it. So it's a right-tailed test by definition. The alternative is greater than, so it's right-tailed. So it's going to be phrased as reject the hoe if t is greater than some number. So right-tailed test will be one-tailed test on the chart. N equals 7. That means 6 degrees of freedom. So 0.01, let me go, 0.01, one tail right here. Right there, one tail, 0.01. Make sure you're in the correct row. 6 degrees of freedom. 3.1427. Let's see how we're doing here. Okay, so there we go. So there's our statement. The test statistic, I kind of just showed it in the calculator here. I'm about to put it in the Ttest process here also. But it's not too hard to calculate with just a regular scientific calculator. 100 minus 95 divided by 4250 divided by the square root of 7. I get 0.3113. So there's 0.3113. And there's the rejection region over there to the right, greater than 3.143. 0.3113 clearly does not fall in that rejection region. It's not greater than 3143. So we fail to reject the hoe. And we do not support the claim that the mean repair cost is more than $95. We do not agree with it. So let's put the calculator to work here. Stat, test, Ttest, number 2. And as I mentioned in the video for Z, the difference between, the hypothesis testings are going to be 1 and 2. Z-test and Ttest, 7 and 8 are the confidence intervals. Because they say interval. Makes sense. Enter. The mu0 was 100. I've already forgot the sample mean. I think it's 95. Yeah. No, 95 is the mu naught we're testing against. Wait, let me double check this. Yeah, more than 95. So that's the mu naught. 100 is the actual sample mean for the data. Standard deviation, I'll double check this, but I believe it's 4250. Now put the actual value of n here. Do not subtract 1. You only subtract 1 for looking up on the chart. Now this is less critical for Ttest than it is for Z-test, only because we're not asking you the p-value, but we might as well just do it correctly anyway. In other words, we're just going to give you the correct test statistic. But I want it to be correct. So this is where you pick the right alternative hypothesis, which for this problem was greater than. But if you're using it like you are for Z-test to get p-values, then you really got to make sure you get this right. But I say get it right anyway. Calculate. And you see, so you can get your test statistic this way if you want to. 0.3113 right there. And there it's showing you the alternative so that you can double check this top line to make sure it matches the ha. That way you know you picked the right one. But even though, you won't be asked for the p-value on these, I would like to bring back up the p-value since we're looking at it. That p-value, 0.383, that's greater than 0.05. 0.01, whatever that is, 0.01. Yeah, whatever. Well, it's greater than any. Whatever alpha is, this is greater. And remember, the rule was if p-value is greater than alpha, you fail to reject. I'm just pointing that out to show you that it backs up our fail to reject answer. So even though you're not going to be asked for that, you still can use that if you need to back up your fail to reject answer right here. Just in case you got the test statistic and you somehow misinterpreted it in the graph and you thought it was reject, you could use the p-value as an assistant there to guide you back to, oh, p-value is greater than alpha, so I know it's fail to reject. All right, very good. AAA claims that the mean nightly lodging rate for a family of 4 traveling on vacation in Florida is at least $185. So at least means greater than or equal to. Therefore, the alternative would be less than $185. Okay. Random sample of 6 such families has a mean nightly lodging rate of $172 with a standard deviation of 15. Is there enough evidence to reject the claim of alpha equals 0.05, assume the population is normally distributed? One thing I want to mention here is that if a problem is giving you the population standard deviation, it needs to clearly indicate either the word population or it can use the sigma symbol, the O with the thing. But the fact that since this sentence is kind of continuing a random sample of 6 families, you would assume that that standard deviation is the sample standard deviation, which it is. So it needs to be, if it's clearly marked, if it's population, it's got to be clearly marked. In this case, it doesn't need to be clearly marked that it's a sample. You would assume that it was. Alrighty. Sample means 172, standard deviation is 15, n is 6. That's going to give me 5 degrees of freedom. Alpha 0.05. This is a left-tailed test, so our chart value will have to be converted to negative when we look it up. So decision rule will be to reject the O if t is less than some negative chart value. So this is going to be one-tailed, 5 degrees of freedom, alpha is 0.05. I'm in the one-tailed. Oh, it's the number right above it here. No, 0.05, excuse me. 0.05, I was thinking 0.01. 0.05. And get myself confused. Yeah. 0.05, 5 degrees of freedom. Right there we go. 2.015 and then 0 at the end. We don't really need, but there it is. So we're going to reject if t is less than negative 2.015. I just didn't put the 0 on there. And you calculate the test statistic. So it's going to be x bar 172 minus the mu naught 185 over 15 divided by square root of 6 is negative 2.123. That's a little bit tricky when they're kind of close on this negative side. I believe I mentioned this in the other video on hypothesis testing, is that you can, just to kind of compare the numbers better, you can flip everything over to the other side. That's kind of what this notation means by taking the absolute values. You're flipping everything over. So you're making that positive 2.105 and you would shade to the right and you make that positive 2.13. Well, if you look at it as positive, then you can see that 2.123 is greater than 2.0125. Which then means if you flip it over and change the signs, this is also true. The negatives can be a little bit tricky on, which side of the rejection region does it fall. But it's clearly reject. So we can run this one through here real quick. Stat, test, Ttest, 185. Was what we're testing against. 172 was a sample mean. I believe this was 15. N was 6. And it was a left-tailed test, so I got to pick the less than right there. So there's the test statistic, negative 2.123. And you can use the p-value if you want to, just to back up whether or not you're going to reject. 0.043 was the p-value, alpha is 0.5. 0.043 is less than 0.05, so that does tie in with the reject. Although if I was a statistician, I'd be a little nervous about this one because it's not exactly a very strong reject, but it would be a reject. So we would go with that. Next example. Leslie claims the average GPA for all UHD students that are sophomore level or higher is 3.0. From a random sample of 22 students, the mean GPA is 2.85 with a standard deviation of 0.8. At a level significance of 0.05, is there enough evidence to reject Leslie's claim? Assume the population is normally distributed. All right, claim sophomore level or higher is 3.0. Is means equal. So it's going to give us a two-tailed test with equal and not equal. So let's see what we have here. So it's going to be equal, not equal, and there's your claim. And so here's the sample data we need. 22 students. That's going to be 21 degrees of freedom. The mean is 2.85, standard deviation of 0.8, and alpha is 0.05. So it looks like, okay, I wrote the rejection. Usually I write the rejection rule first, but I didn't this time. But that's all right, no harm. But I want to go and talk about it first, though. So we're going to have a plus and minus because it's two-tailed. So it's two-tailed, 0.05, 21 degrees of freedom. So make sure we're in the two-tailed, which is this row right here. Two-tailed. So it's, we scroll down, it's the fourth column in. So I'm going to go down 21 degrees of freedom. And there's a magic number, 2.0756. So it's a plus and minus. And let's see what we have. So our decision rule is to reject the hoe if t is less than negative 2.0796 or if t is greater than positive 2.0796. So what we've got to do now is calculate our test statistic. 2.85 is your x bar minus your mu naught, which is 3, divided by 0.8 over the square root of 22. And I get about negative 0.88. And negative 0.88 is clearly not in either rejection zone. It's in the big empty part in the middle, which that's your fail to reject zone. So we failed to reject. There's not sufficient evidence to reject the claim that the mean UHD GPA is 3.0. But as I've talked about before, and it doesn't hurt to say it again, that doesn't mean we necessarily support that claim, that hoe. We just can't reject it. So, and all right, so there it is. I can run this one through the calculator real quick, or let's see, let me keep. Might not do every one of them in the calculator, but I'll do this one just to save time. We'll do it here. I think once you see about 3 of these, I think you'll get the idea. And actually, this will cover all 3 cases because this will be the first two-tailed we've done. Alrighty, so that was 3.0, but 3 is okay, obviously. 2.85. Standard deviation, it's either 0.6 or 0.8. Let me go back and look here. 0.8. 0.8. N is 22. And this is a two-tailed test. Equal, not equal. All right, there we go. So there's your test statistic, negative 0.88. Once again, you won't have to actually get the p-value for these t-tests, but there it is. And it's clearly greater than alpha, so that also means fail to reject. Just want to throw that in there. All right. Local brewery distributes beer in bottles labeled 12 ounces. A government agency thinks that the brewery is cheating its customers with bottles less than 12 ounces. And it's probably not a good idea to cheat people out of their beer. The agency selects 20 of these bottles, measures their contents, and obtains a sample mean of 11.7 with a standard deviation of 0.7. Use a 0.05 level significance to test the agency's claim. Assume the population is normally distributed. So less than 12 ounces. Less than is right there. It's a ha. That means it pairs up with greater than or equal to. So basically, since the claim is the alternative, if we reject the ho, we support the claim. If we fail to reject the ho, we don't support their claim. Now, don't worry about this notation right here. That doesn't really mean anything other than I just do that sometimes where the 0.05 is the alpha, then I put the degrees of freedom. That's all. So this thing that is a t-value at alpha equals 0.05, 19 degrees of freedom because n is 20. So nothing to worry about. You don't have to know that notation or anything. So it's a left-tailed test. It's going to reject if t is less than negative something. So let's go to the chart. 0.05, one-tailed. 0.05, one-tailed, 19 degrees of freedom. So here's 0.05, one-tailed will be this third column. Scroll down to 19 degrees of freedom. Right here. 1.7291. So we're going to reject the ho if t is less than negative 1.7291. So we have 11.7, which is the x bar minus the mu naught of 12 over 0.7 divided by square root of 20. And there it is in the calculator. I'm going to skip the t-test for this one. It's roughly negative 1.92. All we need is enough decimal places to compare it with our chart value. I didn't put that last one there. It doesn't hurt anything. So we have to figure out, does negative 1.92 fall in the rejection zone or in the other zone? Now, once again, you could do, like I said, that other example. You could flip these over and make everything positive. That's what this absolute value is doing. It's the same thing as saying, if you flip everything over, you could see that 1.92 is greater than 1.729, so then you would reject. But you might not have to do that. You might be able to see it just fine like this. Just giving you another way to look at it. So that means we rejected the ho, and we do have sufficient evidence to support the agency's claim that the mean bottle amount is less than 12 ounces. Now, sometimes you might see these smaller samples do this to you here, where it gives you the individual data values. So here's another GPA thing where Big Daddy's claiming the mean for all UHD students is 2.8, and they're actually giving you the 8 GPAs. So what happens here is we're supposed to calculate the sample mean and the standard deviation. So it's not that big of a deal. It just does require a little extra work. But it's not bad at all if you're using the calculator, TI. So there's the claim of equal 2.8 and then not 2.8. So let's get the decision rule first here. So it's 7 degrees of freedom. 0.05 divided by 2 just means two-tailed. So it's two-tailed, 7 degrees of freedom. So let's see if that looks right on our chart. Two-tailed, 0.05, 7 degrees of freedom. $2.3646. Or I just rounded to 2365. But yeah, there it is. It's plus and minus 2.3646. So we're going to reject the hoe if t is less than negative 2.365, or if t is greater than 2.365. Now here, okay, yeah, don't worry about, this is just if you have to do it this way. Well, the mean, you just add them up and divide by 8. But these are just the standard deviation formula that we learned, early in the semester, how to calculate that. But still, even if you don't have the TI calculator, you could still use Excel to do this. I generally don't put these kind of problems on the exam, but I do believe that but I could if I wanted to. Let me make that clear. But I do believe there's maybe one or two of these in the homework, so it's worth taking a look at this example. So that's just using the formula, and you'll see whenever I put it in the calculator that you'll get the same answers I got here. So I get 0.3117 as a rough estimate for the standard deviation, and n was 8. We had 8 numbers, so the mean, the sample mean that I calculated right here was 2.9. So 2.9 minus 2.8 divided by 0.3117 divided by square root of 8 is 0.89. And 0.89 clearly fits between those numbers on the graph, so it's clearly in the fail to reject zone. So that means there is not sufficient evidence to reject the claim that the mean GPA is 2.8. All right, in the calculator, you would have to enter these numbers. Let me come back up here so I can see them easy. I have to put them in a list. Stat, edit. I could type over those, but I'll go up here and hit clear. Then I'll move the arrow and they're gone. And 2.7, 3.3, 2.4. Maybe I should have tried to memorize 4 of them at a time, but I'll just go 3 again. 2, 6, 3, 1, 3, 2. It does help my concentration if I don't talk while I'm doing those, but I don't think you needed to hear me explain what I was doing. You could obviously see it. And the last two are 2.9 and 3.0. And for 3.0, I'll just put 3 in there. That's fine. So we're going to quit out of this. Stat, test, Ttest, data. We choose data when our numbers are in a list. And L1's the default, so that's always good. So we're testing this one, I believe, against 2.8. Let me double check. The other problem was 3.0. 2.8, yeah. So you don't need to enter the mean and standard deviation because that's what I'm saying. It's going to do that for you. And this was a two-tailed test. So we want that to be there. That frequency needs to be 1. I'm not sure what it accomplishes, but it needs to be 1. Calculate. And yeah, see, so there's the sample standard deviation that I calculated that amount using the formula, and this is showing you what it was. So I did it right with using the formula, but here's what we need, the test statistic. And yeah, I got 0.89. What was that one? 0.907. See, so obviously that's just due to some rounding stuff. Obviously I'm right there. I've got it. But yeah, there it is. So like I say, you can see everything right there on the calculator too. So the screen's on there. So, all right. All right, so here's another two-tailed one. Claims the mean lifetime of its fluorescent bulbs is 1,000 hours. Homeowner selects 25 of these bulbs and finds the mean lifetime to be 980 hours with a standard deviation of 80. If alpha equals 0.05, test the manufacturer's claim. And so it's going to be equal, not equal. 1,000. N is 25. Degrees of freedom would be 24. X bar sample means 980. Standard deviation 80. Alpha is 0.05. So that's two-tailed, 05, 24 degrees of freedom. And there we are. We're right there. There's the two-tailed 0.05 column. 24 degrees of freedom. 20639. And I rounded this, but that's okay. Or I might have not changed this problem because I used to use a chart that only had 3 values on it. 3 decimals, I mean. So obviously 3 decimals would have been 2.064. But just be careful. You know, of course, on an exam it wouldn't matter that much, obviously, because you'd be able to pick the right answer. But my math lab homework, it's probably going to, well, it might not. I say it might want 4, it may not. Just as you well know by now, just do whatever it tells you to do. So we're going to reject the hoe if t is less than negative 2.0639. I'll just say it that way. Or if t is greater than 2.0639. So you calculate the test statistic. You get negative 1.25. It falls in the middle. We fail to reject the hoe. And we do not have sufficient evidence to reject the claim that the mean lifetime is 1,000. So we're not rejecting it. But we may not 100% agree with it, or whatever. And here's the whole thing I was just kind of showing you with the negatives and how you can use absolute values to make them positive if you want to. That's not important that you know these rules per se or whatever, but you don't have to worry about these absolute value definitions. But that's what this is doing. When I'm making them positive, we're just putting absolute values on them and comparing it that way. And also you can do these for the same way for z's too, t or z, when you're using the decision rule method. So you can essentially make it positive if you need to try to figure out which one's bigger than the other and where does it fit. Let's take a look at one more example. All right, this will be our last example. A large software company gives job applicants a test of programming ability. 25 applicants are selected at one large university. They produce a mean score of 183, standard deviation of 12. Use a 0.05 level significance to test the claim that the sample comes from a mean score greater than 160. Now, not using a tablet here, I'm going to sort of just kind of write this real rough, then I'll get rid of it. But I probably could have just copied another one from above and just change the number here. But anyway, greater than 160, and that's the claim. So just so I can quit doing this torture here, I'm just going to put less than or equal to right there, but without writing the mu and the 160 there. Okay, there we go. Anyway, so now I'm going to say this verbally here. So we've got 0.05. It's a one-tail test. It's a right-tail test. So it's going to be reject the hoe if t is greater than some positive value from the chart. 0.05, one-tailed, n is 25. That'll be 24 degrees of freedom. Oh, we're already in the right row with 24 degrees of freedom. 0.05 one-tailed is one more column to the left. It's this number. We're going to reject if it's greater than 1.709. So here I'll try another rough-looking sketch here. There's our shading, and I'll just put 1.71 here. So I don't have to try to torture myself with all those. Okay, there we go. So we're rejecting the hoe if t is greater than that number. So let's put this in the calculator. Ttest. Stat. Test. Ttest. Now we're back to stats. Mu naught. One of them is 183. 160 is what we're testing against. So that's your mu naught. Sample means 183. I know n is 25, but I forgot the standard deviation. Oh, it's 12. $12, 25, and greater than. So right there we go. All right, there's your t that you could have easily gotten just by using the test statistic formula. Not too difficult. 9.58. Look at that p-value. That's a really, really tiny p-value with like 9 zeros in front of it. That test statistic of 9.58 is way out here to the right in the rejection land. You know, it's so 9.58. In other words, it's clearly greater than 1.71. So we would reject. And since our claim was the alternative, claiming greater than 160. We do have sufficient evidence to support the software company's claim that the mean test score for all applicants is greater than 160. And that concludes this video on hypothesis testing for the mean, standard deviation unknown.